All right. The last talk before the coffee break is by Vincent Caudrelier, and he's going to speak on Soliton interactions, the Yang-Baxter equation, and the reflection equation.
Thank you, Peter. And yes, so it's a last minute change. Katerina was supposed to talk. You have me instead. I want to thank the other organizers for allowing me to be the backup plan. And hopefully it will go smoothly. So I would like to talk about what's in the title. So presumably the first bit, solid interactions here, everyone will be fine with that. Maybe the Yang-Baxter equation is already a smaller proportion of the audience that's familiar with that. And presumably the reflection equation, the set was even smaller. So hopefully by the end of the talk, I will have worked the whole three things and show the connections between them. And it's actually, more like an overview talk based on old work and more recent work that actually features Katerina and Barbara. You heard some of it, some aspects of it already on Tuesday in Wenchao's talk. These aspects I won't cover too much because he did that. And to motivate the whole thing, I would like to show the video which never ceases to amaze me. So there are two things that we're going to see. This water tank experiment. Soliton traveling. I think this one is probably a good model for KDB, and then it does that first effect. And they send a second one, and the other one is still traveling the other direction. And then we're going to see the more familiar thing of elastic collision in a minute. There you go. So, two things in that experiment that I'm going to elaborate on, and that's kind of the journey of the talk. So here's the plan. Well, the physical motivation is kind of what was in the video, but with some extra decorations, internal degrees of freedom, polarizations, things like that. And then we'll switch to like the mathematics behind these interactions with more degrees of freedom with two main examples, the vector nonlinear Schrödinger or Markov model when you have only two components, one. The more recent one, the complex coupled short-plus equation, which also features very interesting physics and Yang-Baxter equation type things. Then the other main effect is reflection. There's also quite a few things to say about that, and I will try and give you a flavor of that. And then, because it's the conference that it is, hopefully some perspective on what this all means for Soliton gas or GHD. So, well, that was the link to the video. And as I see, so there were two types of processes. The interaction of two solitons, obviously the most common one, and also a very nice reflection without any destruction of the soliton structure of the boundary. So that's, of course, remarkable properties. The first one is the most well-known one, and it survives not only when you have only two solitons, but n solitons. They scatter elastically. These are the flavor of particles, which is kind of the basis of this soliton gas picture. And however, already to describe the other process, so the nice elastic bouncing off the boundary, you have to think a little bit more already in the scalar case. So in the case where the equation of interest would involve a scalar quantity, so the elevation, like in the picture, or for nonlinear Schrödinger equation, the usual complex valued field. And then both of these aspects are even less trivial if you start considering solitons with internal degrees of freedom. And that's where the Yang-Baxter equation and the reflection equation come into the game. So actually, I'm going to give you the answer on how to understand these things, and then I'll tell you how actually you make the links. So these remarkable properties with internal degrees of freedom, and I will give you an example in a minute. The first one, so the elastic collision and the fact that it survives with internal degrees of freedom, is encoded mathematically in a version of the Yang-Baxter equation, so now called the set theoretical Yang-Baxter equation. The parametric denomination is because you have spectral parameter in the background, which again we expect to describe solitons. And that was proposed quite a while ago by Drinfeld, after his even more famous work on quantum groups and quantum integrable systems and possibly groups and everything. So after he got the Fields Medal, well, and then much more recently, and to understand the bouncing of the boundary, with my PhD student at the time, we proposed the kind of companion structure, the reflection equation, which also the set theoretical reflection equation, which captures what's going on at the boundary. Okay, so that's kind of the framework to try and understand what's going on. So now how do you do the calculations and how do you construct such maps and where do you see these equations arise in practice? So before I tell you that, the context, what are they? So first of all, consider in the most general setting a set and a map from the Cartesian product to itself labeled by some two numbers, spectral parameters, we're doing integrable systems with spectral parameters. And then here's the definition of what the set theoretical complexity is. So for those of you who've seen something similar before, it's like a gray group relation. The meaning of the various indices mean that, for instance, this map index 1, 2 only acts non-trivially in the first two factors of the Cartesian product, 1, 3 in the first and third, and number 1, number 2, number 3 later on will become will be interpreted as the zeros of some bigger scattering problem, which determine, for instance, the velocity and the amplitude of your solitons. Okay, so that's a constraint for a map. So it appears in a lot of areas. So generic, but historically, under the name of Yang-Baxter equation, it appeared in the area of quantum integrable systems, also statistical physics, and quantum groups. And in that context, things are a bit simpler or less general. So the set is the vector space, and this Cartesian product is a text product. And then this concatenation means matrix multiplication. But of course, you can fit a lot of different scenarios in this. And for me, the main source of inspiration was Soliton interactions. So that's today's talk. Also, there's a lot of this story going on in discrete integrable systems on lattices. In that area, they're usually known as Yang-Baxter maps, the solutions of this equation. And in that case, usually X has more structure, more geometric structure, as in which has torque, like for instance, it's the projective plane or Riemannians of things. So the other aspect, probably a lot less well known, unless again you know about group theory and Artin groups of B type, but the idea is similar. So now consider just one copy of the, a map on one copy of the set, also parameterized by some spectral parameter. And an accompanying map that acts only on the spectral parameter. And here's the definition of the set theoretical reflection equation for this pair of maps. And this had appeared again before in the quantum world, by the original world of Cherenkov and Zakharov. And but here it's formulated a bit like Drinfeld did in a much more general context on sets, and that's what we need to understand reflections of solitons. So it's a bit abstract at the moment, but we'll see examples of solutions of these things. And they're given to us by, physics, by looking at the interactions of solitons. There's a nice picture that represents the reflection equation. So if you have two bodies, particles, solitons, etc., 1, 2, they can first interact between themselves, and the first one's reflected, then they interact before the second one is reflected. And that should give you the same output with the same result as the other possibility, and that's the content of this equation in a diagram. So the reason I show it now is that there's a nice picture with actual plots at the end that shows you exactly that. So, okay, so examples of integrable equations where Yang have come up to rise. First one, as promised, the vector focusing here, fully focusing because we want to see solitons. Nonlinear Schrödinger equation, and otherwise known as the Malakoff model, which you have only a vector of size 2, and it's amenable to be inverse Caudrelier transform, that's worked. And in particular, because this is pure multi-Soliton solution. So I'm not going to be worried about radiation here because that would, well, because I don't want to, and because then the things are a bit more difficult. But the reason is that there's a fundamental discovery, another one, by Zakharov and Shabbat, so a couple of years after their other important work on the scalar analysis, the dressing method, which is based on the Hilbert formulation of the inverse problem, and just the essence of it, tailored to my needs. So there's a reconstruction formula for some object here, G, X, T, and lambda, which actually we saw in Dionyssis talk earlier. And when you're in the case of pure solitons, so if you build your solution from the vacuum solution, actually the general result is that this object here is a product of elementary dressing factors. Some people call them vacuum matrices or double matrices, different terminology for a similar thing. We saw this idea in Dimitri's talk. Was trying to build solutions on some backgrounds. And that's the generic structure. So there's the identity matrix, these dependence on the spectral parameter. These are the zeros and poles that arise from the scattering, inverse scattering method. And these are the projections, which about that they're the ones that contain the information about the norming. Okay, so mathematically, this object belongs to a rational root group. That was the angle that Wenchai exploited because that's convenient when we want to talk about Hamiltonian structure, because you have the whole theory of Poissonian groups in the background, but I'm not going to talk about that today. So in practice, that's also quite general, but in practice, we have additional symmetries, which are determined from the physical model and which actually pin down the structure of these elementary factors. So for instance, for vector analysis, there is some symmetry that is well known, which sort of is promoted to a constraint or a reduction on this group element, which is like this, which means that in the background for this particular model, you have a unitary group. And in turn, which means that when you look at what it means for the projectors, you find that they're emission projectors. So that simplifies your lives in many ways. The rank one thing is because you work with the vector analysis. It comes from the structure of the lax matrices. So in essentially, all you have to do to understand the multi-Soliton dynamics is to understand these projectors. And the powerful result of Zakharov and Shabbat is that all you need to know is the degeneracy spaces, or if you like, the image of these projectors. So again, taking my favorite example to illustrate the idea. So these are degenerate at special points. In the language of I see the zeros of the spectrum. And then if you specify, so you give yourself a norming axis. So if you specify the degenerate space there, you know what the corresponding projector is, and therefore you get a solution. So that's the summary of the work. So now, okay, now comes the main observation. So you have this object here, which is a product, such elementary assets object, and each such product corresponds to a lambda, so 0. But it's a set; it's not an ordered set. So the element G doesn't care which soliton or which parameter you use first to construct the solutions. So there's a natural action of the symmetric group or permutation group on this object. And that leads to the notion of refactorization, which is crucial to understand Soliton scattering, Soliton interactions in the language of the Yang-Baxter equation. So let me illustrate this idea just for two solitons. So this, all I know is that it's got two values of lambda where it's degenerate with corresponding eigenspaces. But I can first look at the degenerate space at lambda 2 and then at lambda 1, or vice versa, and that will give me the same element. So by uniqueness of this product must be equal to that product. Now, the important thing to realize is that they don't commute in general. So that actually means that these tilde projectors are not necessarily, and they aren't, equal to the non-tilde projectors. So by refactorizing, actually, you end up having a map which is induced by your refactorization problem on the projectors. And remember, the projectors are the quantities that contain the norming constants, so they contain the information about the individual solitons in the mess that is an n-soliton solution. So there's a theorem, there's various variants, and it's been established under various conditions, but essentially the idea is that now, let me give a name to this elementary factor, consider this factorization problem, and then if I give myself the two projectors P1, P2, say, then there is a unique solution for P1 tilde, P2 tilde, and there is an explicit expression. So the summary of this technical slide is the following, is that as a consequence of this refactorization, there is a map, projectors, and which in the case of NLS is a map on projectors of some, well, with the right one, sorry, but you can generalize the argument for other models for the ranks. And yeah, just said that, sorry. So yeah, the map on some projectors which are emission in the context of vector NLS. And now the second step is to show that actually this map is a solution of the separated Yang-Baxter equation. So you could do it brute force with some of the explicit calculations, but that's not the best way to do it. The best way is to actually use the form of the elementary factors and invoke a bit of Newell theorem on the complex plane. And essentially, this is a result of having the equality, sorry, this equality implying the projectors are equal. That's kind of the technical put behind, and it's neater than actually choose things by hand. So I want to pause a moment because although I've been thinking about those things for a while, it still amazes me that you have a Yang-Baxter, quantum Yang-Baxter equation for classical extended nonlinear objects. So yeah, I mean, maybe it's obvious to everyone, but it still amazes me that, you know, it's good. And in fact, what's even more beautiful is not just that it works for scalar solitons. Here, really, because you have these non-trivial projectors, you have internal degrees of freedom as well. And it's quite generic, as I'll show you. So I'll show you just on two examples, but these ideas are much more general than just these two specific examples. So it's very, yeah, it's very pretty. So you can go one step further. You had a map on projectors, and I told you, yeah, it describes really something about the solitons, in particular for vector NLS. It describes their what's known as the polarization vectors. So I don't give you the details, but you can go one more step, and because you know the explicit space independence, thanks to the Zakharov addressing method, you can actually do a bit of long-time asymptotics and extract the information of the polarization vectors that make up the corresponding projector. And okay, I just show you the formula just to show you that it's possible to do it. So if this is the two polarization vectors of your initial solitons far at t equals minus infinity, then they do something, and then they re-emerge with those polarization vectors. And that's the map that tells you what's been going on in the meantime. So you really have a quantum particle scattering picture, but classical objects. Okay. And so that's the story for two, but because you have the Yang-Baxter equation in the background, of course, that ensures the consistency of this picture of factorized scattering for n solitons into a succession of two-body collisions. And that was something that was mentioned by Benjamin this morning in the quantum setup. Okay, so there's a second example. Yeah, still okay. More recent, and that's the work we did with Barbara and Katerina, and it's known as the complex coupled shortness equation. And for me, well, to illustrate the point, the important aspect is that it's also for a quantity that has a vector nature. So 2 degrees of freedom, if you like. So it's not a scalar, it's a vector. And that's why you see non-trivial things of Yang-Baxter maps. So it's amenable to the inverse scattering transform with a lot of very difficult work that Barbara and collaborators did. So they did all the hard work, really. And then we just used this model to reinterpret what was going on in terms of interactions. So one first attraction to this model is that it has a richer Soliton content, even with zero decay manipulations of infinity than vector NLS. So it has things that have been identified by Barbara and the collaborators. So fundamental solitons, fundamental breathers, and composite groups, 3 species of things. So if you want to understand the interactions, you have to consider all the possibilities. You know, what happens if fundamental solitons interact with that, and with that. So that gives us to much more interaction content, and we needed a way to describe this efficiently. And also there was a slight puzzle. So we started to discuss with Barbara. So yeah, that's me when they told me about this problem. It's like, yeah, it's, you know, fun stuff to do and maybe new Yang-Baxter maps. And indeed, so what was the puzzle? So here it's a plot of a fundamental soliton, which is like really your envelope soliton. You can think of it like in LLS. And here you have a breather. So they were incoming. Okay, you have some elastic interaction, but the puzzle was that the fundamental soliton re-emerges as a breather. So it's like, you know, it changes its nature. So how to understand that and how to understand all the possible interactions in the model between the different species of solitons. So, well, the saving grace, which again was discovered by other people and we could just use, is that in fact the lax matrix of the spectral problem is for this model is of matrix NLS type, but size type 4×4, and more importantly, with 2 special symmetries. And that was really what was going on in background. So the first symmetry is the same one as in the vector NLS. So it's the one that tells you that the projectors are going to be Hermitian, and that if you have an eigenvalue in the upper half plane, you also have one in the lower half plane. So that's the standard stuff, if you like. But that's really now a new symmetry, which just happens to be there because of the way the lax matrix is defined and because of the way the fields are put. So this one really did a lot of stuff for us. Okay, we have 2 symmetries, so we use that, and you can repeat all the steps that we had before, the same idea. You have elementary factors, you have refactorization, but now what you have to do is to take into account the symmetries to pin down the structure and the sort of physical context. So we did all this and got some nice, the desired results, the results of description and the mathematical results, the Yang-Baxter maps. So let me quickly show you the results. The first result is that, in fact, instead of having a single elementary factor, the building blocks of that theorem, because of this extra symmetry, are actually made of 2 such elementary blocks, and now that becomes your binary element to work with. Okay, so that's just a fact of life. Still, you have one complex number and one projector that essentially characterize the solution. This other projector is actually related to the first one by the symmetry. So that's all we need. And now how to understand the different types of solution that we had before. It's all encoded in the projector. So if it's rank 1, you cover the 2 possibilities. The fundamental soliton corresponds to the special structure of the image of the projector. So this delta would be like that. And the fundamental breather means it's not special, it's just generic. The one on top. So that's a 4 vector, sorry. 2, 3, 4, 5, 4 entries, split in 2, which is the structure of the lax matrix again. And the composite breather is just when you have a projector of rank 2. So now we can characterize everything according to this. But then the gain is that now all the possible interactions between all the different species, you just have to consider a refactorization problem, but for this composite object, and then take the sub cases. So that's the summary. you use this, you specialize to fundamental soliton, fundamental breather, composite breather, and you have really all the information you like. That's the physical content. The mathematical content is that, as before, because it's the same machinery, the same sort of arguments, we have now a new Yang-Baxter map that acts on different objects. And this slide is just to show you what it looks like in one example. So it's horrible, but when you look at it, I just want to say it's possible. You can compute things. Here they are. And you can compute things in all possible scenarios. So here I picked the scenario that was the puzzle scenario. So here, by exploiting these equations, you can understand what's going on if you have a fundamental soliton and a fundamental breather, because what you have to do is to fix what the deltas, the minus ones are the incoming ones. So you fix what the minus ones are, and we know what to do, how to select them to get either the fundamental soliton or the fundamental breather, and you look at what comes out. So in particular, if you look at this equation, imagine that here I plug just the vector 1, 0, and here you have this mess. There's very little chance that the outcome is going to be 1, 0. It's generated. So that explains why, even if you plug in, we start with a fundamental soliton, the outcome is going to be a breather. So when we had that, we were quite happy because we could understand the origin of this observation. And then what we could do is also to reverse engineer this and just say, well, now we understand really intricately what's going on. You can engineer the parameters of your incoming solitons to do the opposite. So you send two fundamental breathers, you engineer the Darwin constant of one of them in such a way that it comes out as a fundamental soliton. It's kind of the reverse time picture in previous case. So it was good, but well, again, it was, sorry, I'm overexcited because I really like this stuff. So you said, yeah, I have. Okay, so what I'm going to do is skip the reflection things and see if there are questions, because I want to discuss maybe, yeah, that's the reflection equation with solitons. So that's always nice to see. Again, I'm easily amused. But no, I want to give some perspective, because this is a well, I would like to actually, yeah, to share some views with the experts. So this is a conference about, you know, what is it? Oh yeah, Soliton gas, and we had some generalized hydrodynamics this morning, and especially this morning. So there was a very a few talks. People insisted very much on this idea of two-body scattering shift, right? Because this is one of the key building blocks of this whole idea. Well, Gennady originally, and then Benjamin. So how is everything I told you about relevant to this? Well, I need to give you an example. So I'm going to go back to the vector nonlinear Schrödinger and actually show you explicitly what the n-soliton solution looks like at minus infinity and plus infinity, because that's where things are well separated, and that's where you can keep track of what's happened in the meantime. So the setup, as always, you fix the discrete eigenvalues. So that would be the velocity of your soliton J and its amplitude. You order them so that they're well separated in one order, minus infinity and then really much at minus infinity. And then doing straightforward calculations of time asymptotics, you get this. So again, it looks horrible, but what do we see? So first of all, we see that it's a sum of single solutions. Single solitons. The structure here, the scalar structure, is very familiar to the experts. So you've got the envelope, one Book-Bush envelope, the traveling wave at speed 2ui, the phase. But now here we have, because it's a vector NLS, you have a polarization vector. And that wouldn't be there if you had the scalar NLS.
Don't you have the phase also?
That's exactly the point I want to make. It's coming. Yes. Okay. So, and you have the position shift. So, Gennady anticipated. Where is the phase shift? The polarization vector is realize the rules of the phase shift. How do you see that? Because if you look at the formula, it's this vector divided by its norm. In the scalar case, it's just a complex number divided by its norm. It's just a phase. You put it there, that's your phase shift. So the connection that you made is that to understand the phase shift and the position shift in the vector case, you need to understand the Yang-Baxter map, because that's what tells you how these guys are scattered from minus infinity to plus infinity into a succession of
Phase shift that Vienna is referring to is the one included by the delta X.
there are two shifts.
Oh, there are two shifts.
There are two shifts. There's a position shift, the phase
And
shift,
then the left, there are two shifts.
and you see, and the point is that both of them, the position shift depends on this beta plus minus, and the polarization, which is the vector analog of the phase shift, is also beta. And that relation here is what's behind the Yang-Baxter equation. So hidden in there, if you eliminate for the bare norming constants and relate beta plus to beta minus, you see the succession of two
They are not independent.
They're not independent, no. And the map is precisely the vector analog of the product of these phase shifts, scalar phase shifts that are the inputs for all what you guys do. So thank you. That's I think I'm pretty much the wrong person to ask that, because no, I don't know how you perturb. How would you perturb the Yang-Baxter equation? Honestly, sorry, I don't know. I don't know how to approach the question. Generics as in the model or in general? The model. Yeah. So the generic scenario is that if I send a fundamental Soliton with a breather, generically the real merge both has breathers because of the Erwin map I showed you. It's very, being a fundamental Soliton from this point of view is very specific. It's a very special polarization of a fundamental breather. The other way around, so when you send two breathers, maybe that's another way to answer the question, is that if you choose to put the normal constant of one of them in the precise way, then you can make sure that one of them is going to reemerge as a fundamental. So it's very fine-tuned. So it's not generic.
But the generic object in this model is the canonical breather, which
Yeah.
is a superposition of two dominantly polarized canonical breathers.
It's like like two carrier waves. I think you like to describe this with two carrier waves. And the fundamental Soliton is special, it's only one carrier wave survives. So it's not the generic.
And just we have found it for Anna's question, perturbation theory for vector solidus. I mean, you could perturb like a level of the vector solidus and then see how there's it's well established in zero boundary conditions and so much.
So this delta X, it depends on the spectral parameters. Does it also depend on the polarization vector of between common parts?
Yes.
Yeah, there is a question online.
Oh, there's a question online.
On the law. So that's.
So Soliton and user will have to take.
Yeah. You'd have to calculate what the various species.
There's a question online.
Stefan, please unmute your microphone.
Yeah, thank you. Wonderful talk, extremely interesting. I have a question about the symmetry and its interaction with the Yang-Baxter equation. So the symmetry conditions, I would characterize those as equivariance conditions, equivariant symmetries. And I was trying to see how that equivariant symmetry gets encoded or reflected in the Yang-Baxter equation.
Okay, so more. So the symmetries, if you more from the point of view of the reduction group idea of Mikhailov, they're more like they are the action of a group on the action of a group, a discrete group on your loop group, and the symmetry just tells you that the elements of the loop group are in the fixed point subgroup of that action.
But am I wrong to say that the symmetry could be expressed as an equivariance condition?
I don't see the equivariance in the sense that there's a transfer of representation of the group.
Okay.
Or really like a fixed point subgroup condition, as far as I can tell.
Yeah, the reason for asking was just simply to understand the impact of that symmetry on the Yang-Baxter equation, to sort of translate that symmetry over. I wanted a way to see that, the effect of it on the Yang-Baxter equation.
It has is on the type of solution, type of maps. So you see, I had two examples here with slightly different symmetries. So the maps, at the end of the day, when you do calculations, the maps and the objects they act on are a bit different. So you know, and that's where it's more like the type of maps that you can generate from that, rather than, you know, of the Yang-Baxter equation itself. Because that's the equation is the equation. So
Okay.
it has an effect on the set. Yes. It has an effect on the set.
Aha,
when we-
I see. Yeah, okay, a quotienting effect. Thank you. Super.
All right, well, take the rest of the questions in the coffee break because we're supposed to be back here at 4 o'clock. So let's take this.